Hi ladies and gentlemen. So in the last few classes we have understood the ripple counter. Now in that you know that the first flip-flop, the first T flip-flop is clocked by the external clock, and the succeeding flip-flops are clocked by the previous outputs. Now what happens is the clock ripples through this ripple counter, and it takes if there are n stages, it takes n minus so many n minus 1 into delay of one flip-flop for establishing a count. So this is very time consuming. So this can be circumvented if all the flip-flops are clocked together. Okay, such systems are synchronous systems or synchronous counters. So in this video I tell you the design of synchronous counters, design and implementation of synchronous counters. So let me start with that presentation. So the speech is organized into your learning outcomes, then the theory and design of synchronous counters, then a mode 16 synchronous counter with verilog and QUCS. Then we will see the design of a 3-bit LUCAS counter. Then we will implement this LUCAS counter in QUCS and verilog. Then the summary of understanding. So what you will learn, or you will learn the design of synchronous counters, how we develop the excitation table and how we develop the design. Then we will design and you will design and implement a mode 16 synchronous counter using QUCS and verilog. Then you will design and implement a 3-bit LUCAS counter with QUCS and verilog. A LUCAS sequence is something similar to a Fibonacci series. We will see that. Now when you come to the theory and design, in an n-stage synchronous counter, the clock is applied in parallel to all the flip-flops, so that enables simultaneous state transitions. So that results in faster counting or faster operation. The design of the circuit is based on the present state and after the next state. The next state means the state after clock transition. So let us suppose I am designing a mode 16 counter. There are Q3, this is a 4-bit counter. So the Q3, Q2, Q1, Q0, let that be the present state, and Q3 plus Q2 plus Q1 plus Q0 plus, that is the state after the clock. Let us assume this convention. So based on this, I can develop excitation tables and make a design. Now let us look at the truth table of a mode 16 counter, or rather the excitation table of a mode 16 synchronous counter. Here you know that this Q3, Q2, Q1, Q0, this is 0, 0, 0, 0 to 1, 1, 1, 1. This Q3 plus Q2 plus Q1 plus Q0 plus is the next state. So if you look here at the first row, the first count is previous state is 0, 0, 0, 0. The next count is after 0, 0, 0, 0. The next count is 0, 0, 0, 1. That must be written here, 0, 0, 0, 1. So for 0, 0, 0, 1, the next count is 0, 0, 1, 0. For 0, 0, 1, 0, the next count is 0, 0, 1, 1. For the count 1, 0, previous state 1, 0, 0, the next count is 1, 0, 0, 1. This is very simple. You write the next state here, and for 1, 1, 1, 1, the next state should be 0, 0, 0, 0. That is a recent state. Okay. Now if I want to effect a transition from say Q0 to Q0 plus, what should be the value of J0 and K0? Obviously I have 4 flip-flops, and I have to design J3 K3, J2 K2, J1 K1 and J0 K0. The inputs, what are these inputs? They are not just connected to one, as in the case of a ripple counter. They are JK flip-flops. So I have to design for this J3, J2, J1, J0 and K3, K2, K1, K0. Now if you look closely at this Q0, Q0 plus, look at this column and this column. So what should be the value of, because every time there is toggling, here it is Q0 is 0, Q0 plus is 1. So J0 and K0 should be 1. Okay. And likewise here, if you look here, there is toggling everywhere. There is 1 to 0, 0 to 1, then 1 to 0. Here it is some 0 to 1, you can say that it is 1 to 0 everywhere. This toggles when q0 to q0 plus. If you look at this column and this column, you can see that it always toggles. So that means j0 and k0 should be 1. So that is a toggling condition, j0 equal to k0. So j0 column is filled with 1s, k0 column is filled with 1. Now let us look at this q1 and q1 plus. So what should, if q1 and q1 plus 1 plus is available, what should be the value of j1 and k1? So here it is q1 to q1 plus, it is a 0 0. The initial state is 0, the final state is 0. So that means j should be 0, k should be 0, because it is remaining in the previous state. So this j1 and k1 should be 0 0. 0 0 means it is a previous state. And next one, it is q1 is 0 and q1 plus 1, q1 plus is a 1. So there is toggling. So j1 k1 should be 1. Here it is j1 equal to 1, k1 equal to 1. So here again this q1 is 1 and q1 plus 1 is q1 plus is 1, meaning that there is no state change. So j1 k1 should be 0 0. So the next state, it is q1 is 1, q1 plus is 0. So this should be a 1 1, a toggling. So alternately it comes alternately 0 0 and 1 1. You can try for any value. So here it is q1 is 1 and q1 plus is a 0. So that j1 k1 should be 1 1. So here you can see that j1 k1 is 0 0 1 1 0 0 1 1. That way it goes. Now, if you, what is, how do I find the logic for J1 and K1? Either I can resort to a K-map, but you can see that this is very simple. You can compute J1 and K1 just by observation. You can see that J1 is equal to K1 everywhere. J1 is equal to K1. Then what is that? If you look closely with Q0, you can see that this J1 and Q0 are the same. J1 is equal to K1 equal to Q0. You can compare this these two columns, that is J1 and K1, which are same, with Q0. You can see that J1 equal to K1 equal to Q0. Also, I have made two designs. One is J0 equal to K0 equal to 1 and J1 equal to K1 equal to Q0. So this is the first equation, J0 equal to K0 equal to 1, and second is J1 equal to K1 equal to Q0. Now, what are the other things? What about this J2 and K2? So I have to look at, for finding this J2 and K2, I have to look for Q2 and Q2 plus. Okay, what is Q2 here? Q2, the first Q2 is there, Q2 plus is there. Okay, Q2 is there, Q2 plus is there. At first, for first three rows, Q2 does not change. Q2 is 0 0 0 and Q2 plus is 0 0 0. So for the first three rows, this J2 K2 should be 0 0 0 0 0 0 0 0. That is the previous state. For the third, fourth case, this is Q2 is 0 and Q2 plus is 1. So there is toggling. So you can say J2 is equal to K2 equal to 1. And for the next three cases, you can see that Q2 is 1 1 1. Here Q2 plus is 1 1 1. That means that there is no change. So that means J2 equal to K2 equal to 0 0 0 0 0 0 0 0. Here again you can see that Q2 is 1 and Q2 plus is a 0. So there is toggling here. You can see that J2 equal to K2 equal to 1. So that way it is basically 0 0 0 1 0 0 0 1 0 0 0 1 0 0 0 1. That's the way it is happening. Now here also you can see that incidentally J2 is equal to K2. For synchronous counter this needn't be the case, but this being a regular counter from 0 to 16, it happens that way. J2 is equal to K2. Now you can either use a K-map or you can simply observe this and get the design. If you look compare this J2 and K2, J2 and K2 becomes 1 at 4 points, that is here, here and here and here. Here if you look closely you can see that there Q1 and Q0 are 1. Here it is 1 1, here it is 1 1, okay, here it is 1 1, okay, and here it is 1 1. So you can simply by observing you can say that this J2 is equal to K2 is equal to Q1 and Q0, because whenever they both are 1s, you can see that J2 and K2 are 1s. So I have the third equation, J2 is equal to K2 equal to Q1 and Q0. J2 is equal to K2 is equal to Q1 and Q0. Now let us design this J3 and K3. J3 and K3. So what do I do? If I come here, this is Q3 to Q3 plus what is the change? So here it is a 0 to 0, 0 to 0. Here you can see that from here to here there is no change at all. That is from this first row to this row, you can see that there is no change. So that means J3 equal to K3 equal to 0, 0. For all those conditions it is 0, 0. Okay, and here there is a change. You can see that this is Q3 changes from 0 to 1 here, so it is a 1 1. J3 K3 is a 1 1. Everywhere else you can see that it is the same. From here to here you can see that Q3 does not change when it is it becomes Q3 plus, so that J3 equal to K3 equal to 0. And here also there in the last case there is a change, that is from 1 to 0. 1 to 0. So there I have J3 equal to K3 equal to 1. Here also you don't need a comma, because only in two cases you get a 1. So you can see that incidentally you can see that here for that case Q2 Q1 Q0 is 1 1 1 1, and here also Q2 Q1 Q0 is 1 1 1. So what I can easily say that J3 is equal to K3 is equal to Q2 and Q1 and Q0. Q2 and Q1 and Q0. You can see this. J3 equal to K3 equal to Q2 and Q1 and Q0. Now you see this full design. J0 equal to K0 equal to 1, and J1 equal to K1 equal to Q0. J2 equal to K2 equal to Q1 and Q0. J3 equal to K3 equal to Q2 and Q1 and Q0. So this I can develop into a circuit. This is a circuit. So I have 4 flip-flops that are connected to a common clock. You can see that the clock is given in parallel, because this is a synchronous counter. The clock is given in parallel, and for the first flip-flop, of course I keep this preset and clear at 1, so that normal operation is ensured. Initially this J0 and K0, you can see that they are 1s. J0 equal to K0 equal to 1. So I connect this J0 and K0 to 1. This is the output Q0. Okay, this is the output Q0. Now I have the second equation. What is that? J1 equal to K1 equal to Q0. So this is my J1, this is my K1. They are shorted and connected to Q0, because J1 equal to K1 equal to Q0. Now what is this J2 equal to K2? That is Q1 and Q0. Now I add this Q0 and Q1. Okay, this is Q0 and Q1. Then I connect it to J2 and K2. Okay, J2 and K2. Then this output is ANDed with Q2, that is Q2 and Q1 and Q0. This is my output. This is the J3 equal to K3 equal to Q2 and Q1 and Q0. You can say that it is Q2 and Q1, Q0 and Q1 and Q2. This appears as J2 and K2. Okay, so now I can observe this count at Q3, Q2, Q1, Q0. Now I will show you this simulation in QUCS. Now you can see this. Counter. So this is my J0 K0 that is connected to 1. Preset and clear are connected to 1. Clock is given in parallel. It is a 10 nanosecond, 10 nanosecond, 1 nanosecond, 1 nanosecond clock. I am sorry. And here this is Q0 is connected to J1 and K1. This is Q0 and Q1 that is connected to J2 and K2. And Q0 and Q1 and Q2, these are all AND gates. They are connected to J3 and K3. Now let us run the simulation and observe the counting cycles. Now you can see that this counting, this is my clock, and this is my Q0. Okay, this is my Q1. Okay, this is my Q2. Okay, you can see that these counts are 0 0 0. That's a 4-bit thing. It's a 0 0 0. Then it's a 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 1 0 1 0 1. Okay, then I have a 0 1 1 0 0 1 1 1, and then it is eighth count 1 0 0 1 0 0 0, okay, 1 0 0 1 0 0 1 1 0 1 0, and up to, you can see that here it all becomes a 1. You can see that is 1 1 1 1, okay, this is 1 1 1 0. You can observe the truth table also. You can see these counts. For the first clock it is 0 0 0 0, then it is 0 0 0 1, 0 0 1 0, 0 0 1 1, 0 1 0 0, 0 1 0 1, then 0 1 1 0. That way it goes to 1 0 0 0, 1 0 0 1, 1 0 1 0, then 1 1 1 0 1 1, 1 1 0 0. That way down it up counts to, the last count is a 1 1 1 1, then it resets to 0 0 0 0. Okay, so this is how I do the design of a synchronous counter. Now we have verified the operation in QUCS. Now let us see the development in Verilog. So this is a mode 16 counter with Verilog. How do I do that? So what I can do is, otherwise I will show you the code here. This is a mode 16 synchronous counter, and it's test bench. Now this is a mode 16 synchronous counter. Now I'm using the good old edge triggered JK flip flop. So I have to grave include JKF of underscore edge dot v. So this is my file. And I start with a new module say mode 16 synchronous counter with input say output say Q bar, JK as inputs, clock reset, preset they are inputs. So outputs are 4-bit outputs, Q and Q bar are 4-bit wires, and inputs are clock, JK, reset, preset, etc. And I use some internal nets because I have got two AND outputs, so they are A and B are the internal nets. So A is Q0 and Q1, and B is Q0 and Q1 and Q2. Now I have to make 4 instances of the JK positive edge triggered flip flop. Let that be JKF of 0 to JKF of 3. So the first flip flop has an output Q0 and Q0 bar 0, Q0 and Q bar 0. Then this J inputs and K inputs are kept at logic 1, 1B, 1 bit 1. Okay, it's kept at 1. Then clock reset, preset. Then second instance is JKF of posage JKF of 1, say outputs are Q1 and Q bar 1. Then inputs are Q0, J equal to K equal to Q0. So these J and K inputs are connected to Q0, and other things are the same, clock reset, preset, etc. Now this is a third flip flop that is that has an output Q2 and Q bar 2. And what are the inputs to this? This is Q1 and Q0. You can see that it is a AND output of Q1 and Q0. That is A. So that is AA. J and K are AA. Then clock reset, preset. This is fourth flip flop with outputs are Q3 and Q bar 3. What are the J and K inputs? There should be Q0 and Q1 and Q2. What is this? This is B. That is output of the second AND gate. That is it is B comma B, that is J and K are B, and the clock reset, preset. Now I can write a test bench for this. Here this for a synchronous counter. I keep changing the same file. Okay. So this I have to include the newly made module, that is a mode 16 single counter.v, and I started a module, a test bench module, and inputs JK clear preset, they are given as registers, and outputs are given as wires Q and Q bar. Then I make an instance of the mode 16 synchronous counter with these inputs, and then initialize a monitor and all that, just as in the previous cases. Then I dump this to a mode 16 counter.vcd. Then I give these excitation. So initially I clear these flip-flops by applying clear equal to 0 and preset equal to 1. So it starts with the count 0, 0, 0, 0. And then for the remaining time I keep this clear and preset at high so that normal running is ensured. Now I will run this simulation, and you can appreciate this. I can clear this, and I can say I verilog mode 16 counter.v. You can see that it is compiled without any error. Now I run a test bench for this, and -o a dot out. Okay. Now that is also compiled without any error. So I run this executable /a dot out. Now you can see these counting patterns for different clock pulses. So initially this is 0, 0, 0. Initially it is cleared by my clear asynchronous clear, so it becomes a 0. Then when the next clock becomes a 1, it counts 0, 0, 0, 1. Then it is count 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. Whenever the clock becomes high, the state changes. You can see that these counts are from 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0 to 1, 1, 1, 1. After that, it resets to 0, 0, 0, 0. You can see the different counts. This up to 1, 1, 1, 1. After that, it counts 0, 0, 0 and restarts counting. Okay. So you can see this waveform. It's a what you call a GTK wave. .vcd. What is it's mode 16 counter.vcd this way. You can append the relevant signals here, and I can zoom it a little. Now you can see these counting cycles. They are from say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You can say A, B, C, D, E, F. Okay, these are count from 0 to F. Okay, that is 0, 0, 0, 0 to 1, 1, 1, 1. Then it restarts counting 0, 1, 0, 1 that way. Now this is the complemented down counts F, E, D, C, etc. Okay, so this is how I realize a mode 16 synchronous counter with a verilog. Now let me go back to my presentation. Now let us think about another design. Say let us design a 3-bit Lucas counter. A Lucas sequence is something similar to a Fibonacci series, in the sense that the elements are the sum of the previous two numbers from the third time onwards, and it is dissimilar in the sense it is dissimilar to this Fibonacci series in the sense that the first and second times are 2 and 1 respectively. So it starts with 2. Then second value is a 1, so the Fibonacci series starts with a 0, 1, 1, 2, 3 that way. Here this Lucas series starts with a 2 and 1, and then the remaining are the sums, like 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 3 is 7. Now I am making a 3-bit counter, so I stop at 7. So let us design this. Now let us look at this true excitation table. So I have these counts from 2, 1, 3, 2, 1, 3, 4 and 7. These are the 5 counts. These are the 5 3-bit counts. Now this is Q2, Q1, Q0 is 0, 1, 0, 2, 1, 1, 1. And Q2 plus Q1 plus Q0 plus is, after this 0, 1, 0, next count is 0, 0, 1. It is written here 0, 0, 1. It is just a convenient way of writing, nothing more. It is 0, 1, 1. You can use the same table itself. It is up to you. 1, 0, 0, then 1, 1, 1, and the next count is my 0, 1, 0. Okay, so these are Q, and this is my Q plus. Now what should be the value of J2 and K2 for this? How do I say? There is Q2 is changed to Q2 plus. Here there is no change, so input is 0, 0, JK is 0, 0. Here also there is no change, 0 to 0 there is no change, input is 0, 0, JK is 0, 0. Here this 0 is flipped to a 1, so it is a 1, 1, input is a 1, 1, JK. Here no change. Here again there is flipping 1 to 0, so this is 1, 1. Okay. Now what about this J1 and K1 design? This is Q1 and this is Q1 plus. This is 1 to 0, it is a 1, JK is 1, 1, and here it is 0 to 1, it is a 0 to 1, again there is toggling, and it is 1, 1. Here it is again 1 to 0, it's 1, 1. Okay, it is again 1, 1, and here it is the last one, it is a Q1 to Q1 plus, it is a 1, 1, it is a 0, 0. Okay, you can see that it's always 1, 1 except the last case. Okay, now what about J0 and K0? This is, you have to consider the change from Q0 to Q0 plus. This is a 0 to 1 change, so it's a 1, 1. It's a 1 to 0 change, 1 to 1 change, no change actually, so it is 0, 0. Here in the next 3 cases, it's a 1 to 0, 0 to 1, 1, 0. That is a 1, 1, 1, 1, 1, 1. Okay, so this is how J0, K0 behaves. Now I have to design for this J2, K2, J1, K1 and J0, K0. But you don't need a Karnaugh map. If you closely look into this, you can make some easy computations. If you look at these two things, J0 and K0, it is 1 everywhere except for this case. So if you take the complement of this min term, you will get the value of J0 and K0. Here also incidentally J0 and K0 are the same, because we are only considering 1, 1 and 0, 0 cases. So J0 and K0 are the same, and so is J1 and K1 and J2, K2. So if you look here, you can see that instead of doing a K-map, you can easily compute this, because here only it becomes a 0. J0 becomes a 0 here only. So if you take the min time correspond to this, and if you take the complement of that, then it will be J0. So here if you say it is Q2 bar and Q1 bar and Q0, okay. Q2 bar, the min time corresponding to this 0, this is a Q2 bar, Q1 bar and Q0. So if you take the complement of that, it becomes Q2 or Q1 or Q0 bar. Okay, you can see that it is J0 equal to K0 equal to Q2 or Q1 or Q0 bar. I will explain that again. Here it is 0 for this value, for J0, K0. This is the min time corresponding to this 0 value is a Q2 bar, Q1 bar, Q0. So if you take the complement of that, it becomes by De Morgan's law, it becomes a Q2 or Q1 or Q0 bar. Q2 or Q1 or Q0 bar. Now J0 and K0 is that Q2 or Q1 or Q0 bar. Now let us look for this J1 and K1. Here this J1 and K1, again it is everywhere it is 1 except the last case it is a 1. So if you take the min time and take the complement of that, you will get the value for the logic for J1. So what is this? It is Q2 and Q1 and Q0. So the complement of that is all complement. So J1 is Q2 and Q1 and Q0 all complement. It is Q2 and Q1 and Q0 all complement. J1 equal to K1 equal to Q2 and Q1 and Q0 all complement, a 3 input NAND. Now once that is done, we have to design this J2 and K2. If you look closely, what is this J2 and K2? Here you can see that in 2 cases it becomes a 1. So which are these? You can, if you look closely here, you can see that in during that time both Q1 and Q0 are high. So here it is J2 K2 1. You can see that Q1 and Q0 are high. Here also Q1 and Q0 are high. If you look for this J2 and K2, here also Q1 and Q0 are high. Everywhere else one of this Q1 or Q0 is low. So I can easily say that J2 is the same as K2, that is equal to Q1 and Q0. So that completes my design without using any schema. By observing that alone, I can make this design. J2 equal to K2 equal to Q1 and Q0. J1 equal to K1 equal to Q2 and Q1 and Q0 all complement. And J0 equal to K0 equal to Q2 or Q1 or Q0 complement. So with this, armed with these three equations, I can make a circuit diagram, and that looks like this. I need 3 JK flip-flops. So these flip-flops are clocked by a common clock. Okay, these I assume that they are all trailing edge triggered flip-flops. I connect this clock in parallel here. And what about this J0 and K0? Then I connect this preset and clear to 1 so that normal operation is ensured. Then this J0 K0, what is that? J0 K0 is Q2 or Q1 or Q0 bar. That is Q2 or Q1 or Q0 bar. Okay, this is Q0 bar. So this is ORed and applied to J0 and K0. Now what is this J1 and K1? J1 and K1 are Q2 and Q1 and Q0. This is Q2 and Q1. This is an AND gate. Q2, Q0 and Q1. Okay, Q0 and Q1, that is ANDed with Q2. Then this is inverted. This is a NAND. Okay, so this 3 input NAND function, that is Q2 and Q1 and Q0 all complement, that is applied here at J1 and K1. At J2 and K2, what do I apply? That is Q1 and Q0. That is here Q1 and Q0. That is applied to J3 and J2 and K2. I apply Q1 and Q0 to J2 and K2. Okay. So this way I complete the circuit of a 3-bit QUCS counter, and now I can verify this operation by performing a QUCS simulation. Now we can see that this QUCS counter I just designed. So here it is, you can see that J0 equal to K0, that is Q0 bar or Q1 or Q2. And this J1 and K1, what is that? That is Q0 and Q1 and Q2 all complement. Okay. And what is J2 and K2? That is Q1 and Q0. Okay. So once these connections are done, I give a common clock here. This is a 1 nanosecond, 1 nanosecond clock. Now let me run this simulation. You can see that if I simulate, you can see this counting cycles. You can see that initially it is 0 0 0. You start with here it is counting starts. So the first clock it starts at 2. That is a 2. That is 0 1 0. Then 3 0 0 1. Then I have 2, then 1, then we have 3, 0, 1, 1. Then I have 4, that is 1, 0, 0. Okay. Then I have 7, that is 4 plus 3, that is 1, 1, 1. So here also you can see this. This is Q2, Q1, Q0. So here it starts with a 0, 1, 0, that is 2, that is a first count. Okay. 2 is the first count. Then I have 0 0 1, that is a 1, that is a second count. Then I have 0 1 1, that is 3. Okay, 2 plus 1 is 3. Then it is 4, 1 0 0 is 4. Then 4 plus 3, that is 1 1 1. Now again it comes to 0 1 0. Okay, that is a after 1 1 1 it becomes a 0 1 0. So this is how the QUCS counter works. Now we have verified the operation of the 3-bit QUCS counter in QUCS. Now we have to see this operation in verilog. Now I will show you the code corresponding to that. Now this is a QUCS counter. So what I do is, as usual, I include my JK flip-flop. Then I write a new module QUCS, some Q bar, these inputs are specified. Then these outputs are Q and Q bar, a 3-bit output. But here I have to start a selective preset. Here in this last circuit diagram also, if you see, you can see that there is a preset here connected here, so that I can start the operation with a 0 1 0. So I have a selective preset for starting the count at 0 1 0. Okay. So what I do is I keep this preset as a 3-bit wire. Okay. That's an input, a 3-bit wire. Then other things, clock, JK, reset, they are kept as wires. And I have some internal nets ABC as wires, and these are the three logic functions. A is Q bar or Q1 or Q2, so that is applied to the first flip-flop here as J0 and K0. Okay, this A is applied as J0 and K0, and this preset is 0, preset 0, PR0. And for the second flip-flop, Q1 is output, Q bar 1 is a complemented output, and this J and K inputs are B, that is the output of this NAND. What is Q0 and Q1 and Q2 all complement, that is my B. B is applied here, and preset is preset 1, and this Q0 and Q1 ANDed, that is my C, that is applied here. Okay, at the third flip-flop. Now let me write a test bench for this. So that test bench looks this way. Here I include my QUCS counter and I start a module test bench. Then inputs are given as registers, and the preset is given as a 3-bit wire, a 3-bit register, I'm sorry. Then Q and Q bar are outputs, they are specified as 3-bit wires. Then I make an instance of the QUCS counter with these inputs and outputs. Then I run this way. So initially I preset it to 0 1 0. Okay, I have to start the operation with count 2, that is the initial count, that is 0 1 0. So my preset should be, I have an active low preset, so the preset should be 1 0 1. That I give as a 3-bit pattern, 1 0 1. After that the clear and preset are both held at high. And when I apply these clocks, the circuit runs and a dump file QUCS.bcd is returned. Now let us run this simulation and appreciate this. It is verilog .v, and I have QUCS test.v with -o a dot out, the executable. Now it is compiled without any error, so I run this code a dot out. Now you can see these counting cycles. You can see that initially it is reset when I apply the preset 1 0 1 pattern. The flip-flops are preset to 0 1 0. So it starts with the initial count 0 1 0, that is 2. Then the next count is 0 0 1 1. Then the next count is 3 0 1 1. Then 3 plus 1 4, that is 1 0 0. Then I have 4 plus 3 7 1 1 1. Then the next is again back to 0 0 1. After 1 1 1 it goes to the initial count 0 1 0, that is 2. Then 0 0 1, that way it counts. So this is how I develop a 3-bit QUCS counter in Verilog, with Verilog. So with that, let me go back to and I can observe those waveforms in GTK wave. Now in this test bench, I have these signals. Now you can see these counts, they are initially my preset is 1 0 1, so this my flip-flops are initialized to 0 1 0. Then the next count is 0 0 1, then it is 0 1 1, that is 3, then 4 1 0 0, then 7. that is 3 plus 4. Then next is 0 1 0 0 0 1. That way the count repeats. So this is how I develop my 3-bit Lucas counter with verilog. Now let me go back to my presentation. So I'm coming to the end, the summary of understanding. So in this video you learned the design of synchronous counters. Then you designed and implemented a mode 16 synchronous counter using QUCS and verilog. Then you designed and implemented 3-bit Lucas counter. You learned the Lucas sequence series, and you implemented a 3-bit Lucas counter with the QUCS and verilog. And that is the end of this presentation. I thank you all.